Batteries provide direct current, or DC current, that always has the same strength and flows in the same direction. On the other hand, alternating current power sources provide voltage and current with a sinusoidal strength. So a little circle with a little sine wave inside it represents alternating current in circuit diagrams. If you make a graph of either the current or the voltage, you'll see that sometimes it is in the positive direction and sometimes it's in the negative direction. And the instantaneous voltage, so lowercase v indicates instantaneous voltage, is equal to the maximum voltage, which would be the peak of this graph, times the sine of 2 pi ft, where f is the frequency, or the number of cycles per second. And the Vmax is the amplitude of the voltage. So we want to know then, how does this alternating current affect other circuit components? Specifically, let's look at how it affects a resistor. So if we hook a resistor up to an alternating current power supply, then both the current and the voltage will vary across the resistor. So for any instant, we can write down that the instantaneous voltage is equal to the instantaneous current times the resistance of the resistor. Or we can write down that the instantaneous current is equal to the voltage at that moment divided by the resistance. If we make graphs of the voltage across the resistor and the current through the resistor, you can see that these quantities are in phase. So that just means that they're doing the same thing at the same time. When you have the peak voltage, you also have the peak current. When you have the minimum voltage, you also have the minimum current. So how do we express what the average current and average voltage are? If we take the average, and they're both sine waves, the average current and the average voltage are both 0. But that's not really what we want to know. We want to know something about the average strength, and we don't care so much about the direction. So just like we did with air molecules, we find the root mean squared in order to express an average. So if you have a multimeter and you use the multimeter to measure current or voltage, so if you have one and you are using it to measure household current and voltage, which are AC, then the measurement that the multimeter gives you is an RMS measurement. It's a root mean squared value that you're given by your meter. So in order to find the root mean squared value, first you kind of work through that expression backwards. So let's say you wanted to find the RMS current. First you square the current. So if you square a sine wave, then you get another sine wave. But now it's all positive and oscillates between 0 and the square of the maximum current value. Then if you take the mean would be half of that maximum squared value, and then you take the square root of the entire thing to get the RMS value. So since we know that we square the current and then take half of it, and then take the square root of it, that actually gives us a way of translating between the maximum current and the RMS current. The maximum current divided by the square root of 2 is equal to the RMS current. But 1 over the square root of 2 is approximately 0.707. So if you have the maximum current, you can find the RMS current by multiplying the maximum by 0.707. And the same thing works for voltage. If you know the maximum voltage, you can multiply that by 0.707 to find the RMS voltage. So here we can write down that same expression for both current and voltage. And then we can also write down Ohm's law for either RMS quantities or maximum quantities. So Ohm's law applies for AC voltages and currents, but you have to be consistent with the values that you use and make sure that your values are either all maximum values or are all RMS values. What about power? So if you are looking for the instantaneous power, how much power is being used by the resistor at that instant then you can use any of the power equations just with instantaneous quantities. And the fact that these are written in lowercase signifies that these are instantaneous quantities. They are quantities that apply at that instant. If, on the other hand, you want to know the average power consumption, you can use any of these expressions, but with RMS quantities. So using RMS quantities will tell you about the average power consumption for your circuit. So here is another question. Which of the following could be true for a resistor connected in a simple series circuit to an operating AC generator?